A particular coal sample contains 2.12% sulfur by mass. When the coal is burned, the sulfur is converted to sulfur dioxide. What volume of sulfur dioxide measured at 25 degrees Celsius and a pressure of 738 millimeters of mercury is produced by burning 3.5 million pounds of this coal? This is an industrial-sized amount of coal being consumed. The N is hidden in the 3.5 million pounds of coal. We need to use the chemical reaction that was unlisted and the percent by mass values that we have. Sulfur was in the compound, so we're just going to write S as its elemental form, plus oxygen because it's being burned, and we're just going to say that it made SO2. This makes the stoichiometric relationship a 1-to-1-to-1 relationship, which is probably the reason they didn't include it, because it's assumed that you'll have 1 for 1. We are not going to start with our percentage by mass because concentrations like that are conversions. They're going to allow us to move from one thing to the next, from the part to the whole, or from the whole to the part. We're going to go ahead and start with our 3.5 million pounds of coal. And since this is a mass, and if we look at our mole bridge, we'd realize that we need to move from mass to moles. We want to get it into a mass that we're used to using. There are 2.205 pounds for every kilogram. Well, for every kilogram, there are 1,000 grams. So I can go ahead and put these together and do it in one shot, but still reveal that I know exactly what I was doing in order to get the coal amount in grams. Pounds goes away, grams is left, and now I can apply that concentration, the 2.12 grams for every 100 grams of coal. I do know that I said 2.12 grams for every 100 grams. If you'd prefer to write them as percentages, we can, but this is basically the same thing. So for every 100 grams of coal, we would have 2.12 grams of it as sulfur. Again, if you'd prefer to write these as percentages, you can. The percent sign would serve as a unit and would cancel out. Here, grams of coal is gone, grams of sulfur remains, and we're set up to use a molar conversion using the molar mass of sulfur to get to moles of sulfur. There are 32.065 grams of sulfur for every 1 mole of sulfur. After that, using the balanced chemical equation, we know that for every 1 mole of sulfur used, 1 mole of sulfur dioxide would be produced, and this will give us our N value for our ideal gas law. Once we have N, we can feed it into the equation and solve for V. The volume will equal N times R times T divided by P. We now have N. I'm going to go ahead and put in the other conditions of P and T, and then we'll be ready to set up our customized R value. So all of that was N1, and now we're going to put in our temperature of 25 degrees Celsius. We'll have to go ahead and add 273.15 to get it into Kelvin. We'll also go ahead and put in our pressure. Our customized R value needs to cancel out all of the units like Kelvin, millimeters of mercury, and moles. Our customized R value is based off of our mole conversion of 1 mole equaling 22.4 liters at standard temperature and pressure. Standard temperature is 0 degrees Celsius or 273.15 Kelvin. And standard pressure is equal to 1 atmosphere or equivalent. Since this has been using millimeters of mercury, we're going to go ahead and put in 760 millimeters of mercury. This will allow millimeters of mercury to cancel, Kelvin to cancel, and moles to cancel. It will leave liters, which is what we desire, of sulfur dioxide. We'll multiply across the top, divide by the product of the bottom. So when we solve this, we end up with 2.642 times 10 to the 7th liters sulfur dioxide. Again, this was a rather large amount of coal, so it's expected to be a rather large amount of gas. This would be considered our V1 from our equation above.